The continuation of my report, and then last time, if the grain girdle is 30, so we have the formula that this formula. But if it so happen that the constraint, the grain girdle is 83 inches, so we have this constraint G sub mu sub G of x equals 1 plus x minus 83 to the fourth power raised to raised to the negative 1. Then, therefore, the decision, or this is just the the intersection between the two, the objective function and the constraint. So we have membership function we have here x of d equals membership function of x with f and the membership function of g of x to g. Then we have the say condition if this membership function is equal to 0 if x is less than 80 inches, or that is equal to what? The minimum plus this quantity 1 plus x minus 80 to the power of 2 all over this power of negative 1. Then 1 plus minus 1 minus 83 this power of 4 all over raised power of negative 1 if x is greater than or equal to 80 inches. Okay. We go now to the conventional optimization. Say with this equation, we have find x which minimizes f of x subject to the constraint g sub g to the L less than g sub g of x less than or equal to g sub g to the u, or where this L, that is what, lower value, and this u, that is upper value, where this g what starts from the limit 1 to m. Then for the optimization problem, still we have the same condition, but they differ now to this to each constraint. So each constraint now is for the optimization problem. So we have a g sub g of x less than g sub j, where still j equals 1 to m. And with that, where g now, that is your Fuzzy, is our Fuzzy interval to which the function g sub j of x should belong, or meaning this one should belong, meaning this is what is another way of stating this one, that is j of x, that is just the element of g. Okay. Then we have a membership function of x with respect to s, that is equal to the minimum of mu sub j of g times this j of x, where j again, that is equal to 1 to m. Okay, therefore the design vector is considered feasible when membership function of x with respect to s is greater than 0. So meaning, if this one, it should be what? A positive value because it's greater than 0. If it so happen that this is less than, so therefore, we cannot come up with the right decision. So no decision, so meaning no solution at all. And to have this graph of this design vector, for example, we have here a graph from 0 to x. So x ends, x inches, or we have here that is 0 to 1 for the mu. Therefore, this graph, the solid line of this graph, this is what? That is the constraint. This one is the constraint. And this one is cutting line, that is your objective functions. Then we have decision, or the design variable, it should be, in this case, the solid one. Remember, the decision, it should be what? Inside with this, say, constraint and the objective function. And take note that this, the design variable, what? It never touches to this duty function graph. Wala siya na-touch. As well as this one, constraint, this one. Wala, it never touches. Wala siya na-touch there. So, this is now the graph. Okay, for the computational problem, so it is similarly or slightly the same as this conventional optimization and optimization problem, but only they differ only with what? With lambda. With lambda, this new variable. We have here example, if you're going to find x and lambda which minimize lambda. Okay, subject to the constraints, lambda which is less than or equal to the membership function x f or the objective function, and we have here again lambda that is less than or equal to objective function of say x with g of g with lower bound. Okay, where g again is equal to 1 to m. And we have again for the upper bound lambda less than or equal to membership function of x of g j to the upper value where g equals 1 to m. Okay.